Hello, my name is Ashish Udgave. I am working as an assistant professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Yadav. I am welcome to all in the lecture of Work, Power and Energy. Please note that now onwards we will study module number 4 Kinetics and module number 5 Kinematics simultaneously. In last video, we have covered the concept of D'Alembert's principle and have solved problems on D'Alembert's principle. In this video number 10, we are going to cover concept of work energy method and problems on work energy method. In the last video, kinetic problems were solved using D'Alembert's dynamic equilibrium condition. In this video, another approach called work energy approach is used to solve kinetic problems. This method is advantageous over D'Alembert's method when the problems involves velocity rather than acceleration. The terms work, energy and power are explained first, then the work energy equation is derived. Using this equation, a number of kinetic problems were solved. Number 1. Work. The work done by a force on a moving body is defined as the product of force and the distance moved in direction of the force. In the above figure, various forces acting on a particle are shown. If the particle moves a distance s in x direction from A to B, then the work done by various forces are as given below. From the figure, suppose force P1 is acting towards right direction and the displacement covered was s. As force and displacement both are in same direction, therefore work done by force P1 is equal to P1 into s. Now work done by force P2 is acting towards horizontally left direction and displacement is towards horizontally right direction, therefore both are in opposite direction, therefore work done by force P2 is equal to minus P2 into s. In the same way, work done by force P3 is equal to 0 as displacement in upward direction should be 0, and work done by force P4 is equal to P4s into cos theta. The general expression for work done by force P is Ps into cos theta, where theta is the angle between the force and the direction of motion. This expression may be rearranged as P cos of x into s, giving the new definition of work done. Thus, work done by a force may be defined as the product of component of force in the direction of motion and the distance moved. From the definition of work, it is obvious that unit of work is obtained by multiplying unit of force by unit of length. Hence, if Newton is the unit of force and meter is the unit of displacement, therefore unit of work will be Newton meter. 1 Newton meter of work is denoted by the term joule. Hence, 1 joule may be defined as the amount of work done by 1 Newton force when the particle moves 1 meter in the direction of that force. The other commonly used units are kilojoules or millijoules, etc. Energy. Energy is defined as capacity to do work. There are many forms of energy like heat energy, mechanical energy, electrical energy and chemical energy. In engineering mechanics, we are interested in mechanical energy. This energy may be classified into potential energy and kinetic energy. Potential energy is the capacity to do work due to the position of the body. Suppose a body of weight W held at height h, then potential energy of that body is equal to W into h, or in terms of mass, potential energy is equal to mgh. Kinetic energy, it is capacity to do work due to motion of the body. Formula for kinetic energy is that kinetic energy is equal to 1/2 mv square. Therefore, kinetic energy is equal to 1/2 into W upon G into V square. Unit of energy is same as that of work since it is nothing but capacity to do work. Therefore, it is measured in joules or kilojoules, etc. Power is defined as time rate of doing work. Unit of power is watt and is defined as 1 joule of work done in 1 second. In practice, kilowatt is commonly used unit which is equal to 1000 watts. Horsepower is the unit used in MKS and FPS systems. 1 British HP is equal to 735.75 watts and 1 British HP is equal to 745.8 watts. Law of conservation of energy. It states that the energy can neither be created nor be destroyed, though it can be transformed from one form to another form. The second statement of this law is that the total energy possessed by the body remains constant provided that no energy is added to or taken from it. Suppose a body of mass m is at resting on top of the tower of height h. Figure shows the body of mass. The figure shows the body resting on top of the tower. Let W be the weight of the body, M be the mass of the body. We know that W is equal to mg, therefore M is equal to W upon g. And height h. Let us find, first of all, let us find the potential energy and kinetic energy of the body at the top of the tower. We know that potential energy is equal to W into h and kinetic energy of the body is equal to 1 half mv square. Since body at the top of the tower body is at rest, therefore kinetic energy of the body must be 0. Therefore total energy at the top of the tower is equal to kinetic energy plus potential energy. Therefore total energy at the top of the tower is equal to W into h. Now suppose the body falls down by height h1 to the position 1 1 as shown in figure. Let v1 is the velocity at position 1. We know that v square minus u square is equal to twice as. Therefore that equation becomes v1 square minus u square is equal to twice g into h1. Therefore we get v1 square is equal to twice g into h1. Now kinetic energy of the body at position 1 is equal to 1 half m v1 square. We know that v1 square is equal to twice gh1. Therefore we get kinetic energy of the body at position 1 is equal to W into h1. Now potential energy at position 1 1 is equal to W into height of the body from height of body at 1 with respect to ground. We know that height of that body at position 1 is equal to h minus h1. Therefore potential energy at position 1 is equal to W into h minus h1. Now total energy at position 1 is equal to potential energy plus kinetic energy. Therefore we get total energy at position 1 is equal to W into h. It is the same energy the body was possessing at the top of the tower. Similarly, it can be proved that total energy of the body on the ground will be equal to W into h. Work energy equation for translation. Consider the body shown in figure subjected to system of forces F1, F2 plus and so on and moving with an acceleration a in x direction. Let its initial velocity at a be u and final velocity when it moves a distance ab is equal to s bv. Then a resultant of the system of forces must be in x direction. Let as body moves towards right direction or x direction, then resultant force must be at towards x direction. Therefore R is equal to summation Fs. From Newton's second law of motion, we know that R is equal to ma. Therefore R is equal to W upon g into a. Multiplying both the sides by an elementary distance ds, we get R into ds is equal to W upon g into a into ds. Since a is equal to acceleration is equal to v into dv upon ds, therefore we get R into ds is equal to W upon g into v into dv upon ds. Therefore R into ds is equal to W upon g into v into dv. Integrating both sides of the equation, integrating both the sides for the motion from a to b, we get integration of R ds, limits from 0 to s, is equal to integration of W upon G into V into dV, limits from U to V. Therefore, we get R into S is equal to W upon G into V square upon 2, where limits from U to V. Therefore, we get R into S is equal to W upon twice G into V square minus U square. Now, R into S is the work done by the forces acting on the body. W upon G into V square is the final kinetic energy, and W upon twice G into U square is the initial kinetic energy. Hence, we can say that work done in a motion is equal to change in kinetic energy. That is, work done is equal to final kinetic energy minus initial kinetic energy. It is called as a work energy equation. This work energy principle may be stated as work done by a system of forces acting on a body during a displacement is equal to change in its kinetic energy of the body during the same displacement. Problem number 1. A body weighing 300 Newton is pushed up a 30-degree plane by 400 Newton force acting parallel to the plane. If the initial velocity of the body is 1.5 meter per second and coefficient of kinetic friction mu is equal to 0.2, what velocity will the body have after moving 6 meters? In this problem, given entities are weight of body 300 Newton, inclination of plane 30 degree, and here a body is moving 30 degree 300 Newton. A body weighing 300 Newton is pushed up a 30 degree plane by 400 Newton force acting parallel to the plane. Therefore, this figure shows free body diagram of 300 Newton body. Weight of body is acting towards downward direction. As body moves in upward direction, therefore force of friction must be in downward direction. Normal reaction N perpendicular to the supporting surface. Now consider a free body diagram of the body shown in figure. Summation of forces normal to the plane, that is summation Fx is equal to 0. We get N is equal to 259.81 Newton. Since we know that frictional force F is equal to mu into N, therefore we get F is equal to 51.96 Newton. Now initial velocity U is equal to 1.5 meter per second and displacement S is equal to 6 meters. Let the final velocity of the body be V meter per second. Equating work done by a force along the plane and change in kinetic energy is equal to change in kinetic energy, we get 400 minus F minus W sin theta into S is equal to, that is work done is equal to 1/2 into W upon G into V square minus U square. From that we get V is equal to 8.942 meter per second. Since in this above equation, as body is moving in upward direction, therefore all the horizontal forces acting towards right direction are taken as positive, and all the horizontal components acting towards left direction are taken as negative. Therefore, answer of the problem: velocity of the body after moving 6 meter V is equal to 8.942 meter per second. Now next problem: a block weighing 2500 Newton rests on level horizontal plane for which coefficient of friction is 0.20. This block is pulled up by a force of 1000 Newton acting at an angle of 30 degree to the horizontal. Find the velocity of the block after it moves 30 meters starting from rest. If the force of 1000 Newton is then removed, how much further will it move? Use work energy method. In this problem, a block of 2500 Newton rests on a level ground and coefficient of friction mu is equal to 0.20. This block is pulled up by a force of 1000 Newton acting at an angle 30 degree to the horizontal. Therefore, free body diagram of the figure is given in figure A. Since Block is moving towards right direction, therefore force of friction must be towards left direction. Weight of the body acting in downward direction, and normal reaction must be perpendicular to the supporting surface, that is exactly vertically upward direction. Free body diagram of the block for two cases are shown in figure A and B. Now considering case A, when pull P is acting, applying summation Fy is equal to 0, we get N is equal to 2000 Newton. Since we know that F is equal to mu into N, therefore we get F is equal to 400 Newton. Since initial velocity of the body as body starts from rest, therefore initial velocity of the body is 0, and let V be the final velocity of the body. Displacement S is equal to 30 meter. Applying work energy equation for horizontal motion, we get P cos of 30 minus F into S is equal to W upon twice G into V square minus V square. That is, according to work energy equation, change in work done by body is equal to change in kinetic energy. Therefore, we get V is equal to 10.4745 meter per second. Now, if case second, if the force 1000 Newton is removed, let the distance moved be S before the body comes to rest. Therefore, initial velocity of the body u is equal to 10.4745 meter per second, and final velocity of the body must be 0. Now, applying work energy equation for the motion of in horizontal direction, we get minus F into S is equal to W upon twice G into V square minus U square. Therefore, we get S is equal to 27.96 meter. Therefore, answer of this problem: velocity of the block after it moves 30 meter starting from rest, V is equal to 10.4745 meter per second, and if the force of 1000 Newton is removed, then the block will move 27.96 meter. Last problem: two bodies weighing 300 Newton and 450 Newton are hung to the ends of rope passing over an idle pulley as shown in figure. How much distance the block will move in increasing the velocity of the system from 2 meter per second to 4 meter per second? How much is the tension in the string? Use work energy method. In this problem, 450 Newton block moves down and 300 Newton block moves up. The arrangement is such that both bodies will having the same velocity and both will move by same distance. Let S be the distance moved. Writing work energy equation for the system, we get 450 into S minus 300 into S is equal to 450 divided by 2 into 9.81 into V square minus U square plus 300 divided by 2 into 9.81 into V square minus U square. Since in this problem 450 Newton block moves in downward direction and 300 Newton block will move in upward direction. Therefore, we get S is equal to 3.058 meter. Now, considering 450 Newton block only, refer figure B. In this figure, weight of 450 Newton block is acting in downward direction, and let T be the tension in the string which is in upward direction. Now consider work energy equation for any body, say 450 Newton body as shown in figure B. We get 450 into S minus T into S is equal to 450 divided by 2 into 9.81 into 4 square minus 2 square. Here body is moving in downward direction, therefore downward direction forces are taken as positive, and and upward direction forces are taken as a negative. Therefore from this equation we get T is equal to 360 Newton. Therefore answer of this problem: the blocks will move in increasing the velocity of the system from 2 meter per second to 4 meter per second. S is equal to 3.058 meter, and tension in the string T is equal to 360 Newton. Please note that this video is prepared for academic use only. To understand the concept of work energy method, and to solve the problems related to work energy method for UG students only. Thank you. Thanks a lot. For any query, please feel free to contact me on mail or on mobile. Thank you.